Make neural nets learn the right way with activations. You will learn what Sigmoid, Tanh, and ReLU actually do. You will see small Python examples that visualize behavior and build a tiny Sigmoid classifier. You will know when to pick each activation and what to watch for during training. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Activation functions decide how a neuron responds to input. They let networks solve nonlinear problems instead of just scaling inputs. In practice, people reach for Sigmoid or Tanh for smooth, bounded outputs, and ReLU for sparse and fast training. A common downside is that some functions can saturate or die, which hurts training speed compared to alternatives that keep gradients flowing. Think of a linear model as a straight road and activations as forks that let us leave the straight path and reach new destinations. Intuitively, Sigmoid is the S-shaped squasher that maps numbers between 0 and 1. Tanh is similar, but maps between -1 and 1 and centers outputs at 0. ReLU stands for Rectified Linear Unit and outputs 0 for negatives and keeps positives as they are. A quick mini example is imagining a neuron that sums input, multiplies by weight, and then applies one of these functions. The weight changes how steep the curve looks, and a bias shifts the curve left or right. We will build 5 focused examples that demonstrate these effects and end with a tiny classifier we can measure. This snippet maps toy inputs through the Sigmoid activation to show bounded outputs. It feeds a short list of sample numbers into Sigmoid and prints the results, so you can hear the pattern. Small negative inputs collapse near 0. Large positives approach 1, and values close to 0 sit in the steep middle where gradients are largest. The example highlights how scaling an input by a larger weight makes the Sigmoid switch from gentle to very steep, and how that steepness influences how quickly a neuron changes during learning. Next, we inspect a neuron that combines weight and bias before a smooth squasher. This example applies Tanh to a linear neuron output built from weight and bias. It multiplies the input by a weight, adds a bias, and runs Tanh to show symmetric outputs around 0. The demo makes it clear that a negative bias can push outputs toward -1 and a positive bias toward 1. If you increase the weight magnitude, the Tanh curve becomes steeper and outputs saturate faster. Because Tanh is 0-centered, it often gives gradients that balance positive and negative signals better than Sigmoid. Now we compare activations head-to-head on the same inputs. This code ranks ReLU, Sigmoid, and Tanh by their mean activation on shared inputs. It runs the same batch of numbers through each activation and reports average values, so you can see practical differences. ReLU typically yields a higher mean for positive biased inputs and many zeros for negative inputs. Sigmoid produces values strictly between 0 and 1, and Tanh sits between -1 and 1 with a centered mean. That ranking helps reveal sparsity from ReLU, saturation tendencies in Sigmoid, and balanced outputs in Tanh. Next, we explore how bias moves Sigmoid into or out of saturation. This snippet shows how shifting bias affects Sigmoid saturation on the same inputs. It keeps inputs identical and adjusts bias to push neuron outputs left or right along the Sigmoid curve. When bias drives outputs into the flat ends, the gradient magnitude drops and learning slows. Small bias changes can keep a neuron in the useful steep region so it learns quickly. The example emphasizes that initial bias and how you update it are simple levers that change where neurons operate on the activation curve. Finally, we put Sigmoid into a tiny classifier and report a metric. This code builds a tiny Sigmoid classifier and reports its accuracy on toy data. It trains a single neuron with Sigmoid output as a probability, and then thresholds predictions to make class decisions. Accuracy, which measures the percentage of correct predictions, shows how well the trained neuron separates the toy classes. The snippet also exposes how learning rate and number of training steps affect final accuracy. Too large a learning rate can oscillate and hurt accuracy, while too small a rate slows progress. After those concrete examples, let us summarize practical training tips. Initialize biases so neurons start in their sensitive regions rather than saturated extremes. For hidden layers, prefer ReLU when you need speed and sparse activations, and prefer Tanh when you want zero-centered outputs that can stabilize gradients. Use Sigmoid at the final layer for binary probability outputs, but avoid it for deep hidden layers where vanishing gradients matter. Also, watch adjustable parameters closely. Increasing weight scale makes activation steeper and can cause saturation. Changing bias can move neurons into either dead or active zones. Tweak learning rate and run a few trials with small toy sets to get an intuition before scaling to larger data. Recap in 3 points. What it is. Activation functions turn linear sums into useful nonlinear signals. When to use it. Use ReLU for fast hidden layers, Tanh for centered outputs, and Sigmoid for final binary probabilities. One caveat, watch for saturation and dead neurons, which slow or stop learning. Next step, extend these tiny experiments by training the same small network on a larger synthetic dataset. And measure accuracy and training time as you swap activations and tune learning rate. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.